So in this lesson, we're going to continue our discussion on solving systems of equations, right? So we started a discussion by going through the first technique, which was the naive Gauss elimination, and we explained why it was called the naive. Because in certain cases, we have certain matrices that when we're creating the factor, we can divide by zero, and we remedied that problem by introducing a concept called pivoting, which is just merely swapping rows using the concept of the highest absolute value. Okay, now we're going to go through our next technique. The next technique is doing it through Gauss-Jordan. Now, if you remember with Gauss elimination had two main processes in it. We do forward elimination, which is basically creating those zeros at the bottom left, and then we did backward substitution, right? We got x3, x2, x1, and this is why it's called backward substitution, because instead of getting x1, x2, x3, we're going it from the back. We're doing x3, x2, x1. So those are the two processes in Gauss-Jordan: forward elimination, backward substitution. So what about Gauss-Jordan? Well, Gauss-Jordan is different from Gauss elimination. It actually has three processes involved in it. The first one is much similar to, or identical actually, to the Gauss elimination, which is forward elimination, right? So in Gauss-Jordan, the first thing that we do is the same thing that we do with Gauss elimination. We create those bottom three zeros. Okay. Now with Gauss-Jordan, now instead of going to backward substitution as with the Gauss elimination, we're going to go through something called backward elimination, which comes from which is similar to forward elimination, but instead of creating the bottom three zeros here, we're creating the top three zeros here. So after we undergo the backward elimination, we should have the top right corner is very similar to the bottom left corner, right? So this is what is called backward elimination. So forward elimination, we're going forward and we're creating those two zeros and then this zero, and backward elimination, we're creating those two zeros, then this zero. Now, the third process in Gauss-Jordan is normalization. And normalization, basically, you take this A11 and you normalize the entire row by it. And what I mean by normalizing, you divide everything in this row by that number, right? So if I take this number 1, I'm going to divide 1 divided by 1, 0 divided by 1, 0 divided by 1, negative 0.25 divided by 1. And I'm going to, for normalizing the second row, I'm going to take this A22, take 0 divided by A22, negative 4 divided by A22, and 0 divided by A22, and 2 divided by A22. And you can kind of predict what we're going to do for the third row. The third row, we're going to take A33. I'm going to take 0 divided by A33, 0 divided by A33, and this number divided by A33, and 27 divided by A33. Now you can see, okay, I'm taking, why not just divide this number by A11 and this number by A11, and those two, we don't divide them since they are zeros. Well, there is a way we can actually make the code efficient to not divide by these, but for the sake of simplicity, we're going to keep the code or the process dividing those numbers by, in this case, A11, and those two by A22, and those two by A33. So the first thing I want to go through here is the difference between the process of doing Gauss elimination, which is forward elimination, backward substitution. Those are the two processes in Gauss elimination. Now, when it comes to Gauss-Jordan, as we explained here, there are three processes, right? We have forward elimination, creating those three zeros, backward elimination, creating those three zeros, and then normalization, basically dividing this entire row by A11, dividing this entire row by A22, divided this entire row by A33. Now, I want you to see something. When we used to do backward elimination, this is A33, which is going to be equal to 2.25. And if we say 0 times x1, 1 times x2, 0 times x3 is equal to negative 0.5, you're going to find that x2 is going to be equal to negative 0.5. And this is going to be 1 times x1, 0 times x2, plus 0 times x3 is equal to negative 0.25, you're going to find that x1 is equal to negative 0.25. So if I went through forward elimination, backward elimination, and normalization, whatever I have on the left hand or the right hand side are my solutions, right? So these are x1, x2, and x3. So this is the great thing about Gauss-Jordan, that if I go through forward elimination, backward elimination, and normalization, whatever I have on the right hand side, those are going to be my solutions. Okay, so let's actually go ahead and go through the code of how to actually write a Gauss-Jordan. And it's actually very, very similar and very simple. If you know Gauss elimination, this is not going to be an issue at all to learn. This is the matrix that I'm going to be dealing with. So I have x1 plus x2 minus x3 is equal to negative 3. So that's the first one. So by extracting the coefficients from here, so we have 1, 1, negative 1, and negative 3. And this is going to be 6, 2, 2, 2. So 6, 2, 2, 2. And that's negative 3, 4, and 1, and 1. So you can see this is the coefficient matrix A, and this is the vector B. Now, when we're coding, the first thing we basically dimensionalize, right, our array. And what I'm going to do is, instead of making an array for A and making an array for B, I'm just going to store them all into one. So I have here a 3 by 4 matrix. Okay, so I did A is 3 for columns, or for rows, and 4 for columns. Now, then we're going to, first thing that much like we did with the Gauss elimination, we're going to input our values inside this array by referencing them to those cells and columns. So it's going to be A, I, J, and this is going to start at the 11th. So it's going to be 10 plus I, and this is going to start at the 7th column, so 6 plus J. So this code is to input the values. Given that we inputted the values, we have 3 processes that we need to go through, right? We need to go through forward elimination, then we need to go through backward elimination, and we need to go through normalization. Now, to kind of review what we did with Gauss elimination, so this is the same identical forward elimination code that we dealt with. So we have k is equal to 1 to 2, and we explained why it's 2 rows, right? So, sorry, it's 2 loops. The first loop is going to create those 2 zeros, and the second loop is going to create this 0. Right? So we said for I is equal to k plus 1 to 3. So when k is 1, that's going to be from 2 to 3, which means this is going to loop twice, right? And when this is going to loop twice, we're going to create those 2 zeros, right? And then we're going to go to k equal 2. Now when k is equal to 2, 2 plus 2 is 3, 3 plus 3, that's going to loop only once, and it's going to loop only once because we're creating only 1 0 after that. Now, if you remember with the forward elimination, we create the factor, right? And then we apply this factor using this loop here. So what we do is we take this number minus the factor times 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 this number. And also to create the 0 down here is this factor minus the number times this factor minus the, this number minus the factor times this number minus the factor times this number minus the factor times this number, and you kind of get the idea. So this is kind of to recap what forward elimination does. Now with backward elimination is very, very similar or almost an identical code. The only thing that changes from a code for a forward elimination to a code of a backward elimination is how you define the loops. So here I defined it k is equal to 1 to 2. This is k is equal to 3 to 2, step of negative 1. So this is, we're going backwards, right? Backwards and creating those 3 zeros. So that's why, so it would make sense. We're going to go from 1 to 2 to 3 to 2. Now this one, instead of from k plus 1 to 3, is going to be k minus 1 to 1. And again, if you're going to do anything but increase by an increment of 1, you have to use the step keyword. So in this case, we're going down by 1. So it's going to be step of negative 1. And you can see this factor line is the same line of code here, and this loop is the same loop that I have here. So the only thing that changed from a forward elimination code to a backward elimination code is that the first loop, k changed from k is equal to 1 to 2, and now is k is equal to 3 to 2. And this I loop, it changed from k plus 1 to 3 to k minus 1 to 1. Okay, so that's the only change between a forward elimination code and a backward elimination code. And kind of to recap, forward elimination, we're creating those 3 zeros, and backward elimination, we're creating those 3 zeros. Okay. Now with normalization, like we said with normalization, what we're doing is we're taking A11, we're dividing everything in every value in this a row by A11. We're taking A22, everything in this second row by A22, and taking A33, and in the third column dividing everything by A33. So here's the normalization code. We're going to have a nested loop. So it's going to be I is equal to 1 to 3 because we have 3 rows, and we're going to have j is equal to 1 to 4 because we have 4 columns. Before we get into the columns loop, we have to define the pivot. So the pivot is going to be AII. So for I equal to 1, so the pivot is going to be A11, so which is basically this value here. Then we're going to go in here. We're going to say that A11 is equal to A11 divided by A11. Then for the second loop, it's going to be A12 is equal to A12 divided by A11. And for the third one, A13 is equal to A13 divided by A11. And for the fourth one, it's going to be A14 divided by A14 divided by A11. So you can see that with this code, I took A11 and divided everything in this row by it. Now we go to the second I loop. That's going to be, now the pivot is going to be A22. So now we're going to go to A21 is equal to A21 divided by A22, and you kind of get the idea. And for the third loop, this is going to be A33, and it's going to take every single value in the third row and divide it by A33. So now we normalized, right? So now this is a line of code that is going to display. So it's going to take these values from here, and these are ones that I manually put in. So this is kind of to see what the code is actually doing. That in the first loop here is creating this 0, then is creating this 0, then it's creating this 0. And with the backward, it first creates this 0, then it creates this 0, then it creates this 0. And after normalization, we have this. Now, the one thing I want you to notice is that we described this type of matrix. This is called a identity matrix. So you can see what the Gauss-Jordan does. It takes the A matrix here, right, the augmented A matrix, and it turns it into an identity matrix. And by turning it into the identity matrix, the B vector, which is the right-hand side here, becomes our solution. So that's the entire idea of the Gauss-Jordan. We're taking the coefficient A matrix, turning it into an identity matrix, and by consequence, the right-hand side becomes our solution. Okay, so let's actually go ahead and delete this, and let's run the code. So what the code is going to do, so we're going to create that A 3 by 4 matrix. We're going to input the values. We're going to go through the 3 processes in Gauss-Jordan: forward elimination, backward elimination, and normalization. After we normalize, we are going to go ahead and display the entire matrix, 4 by 4 matrix. And we know that the right-hand side, if we go through forward, backward elimination, normalization, is going to be, or are going to be, our solutions. So let me run the code. All right, perfect. So you can see that I took these values from here, and I've undergone all these processes. I created my identity matrix, and now here are my solutions. This is my x1, x2, and x3. So it's a pretty simple process. It does the same thing as Gauss elimination. It's just another way of doing it. Again, to recap, Gauss elimination, you do forward elimination, backward substitution. Okay. Now with Gauss-Jordan, you go with forward elimination, backward elimination, and normalization. Now, this is the second technique that we gone through for solving systems of equations. Now, in future lessons, we're going to go through another technique. It's called LU decomposition, and this is going to be a pretty interesting technique because this is usually a technique that is used to get something that is called an inverse matrix, and we're going to explain what that is. It's a pretty interesting concept. But that's it for this lesson, and I will see you in the next lesson.